Good afternoon, this is Ring Newland from the Academic Medical Center in Amsterdam. I would like to tell you something today about the isolation of extracellular vesicles. In particular, I would like to discuss size exclusion chromatography. Now, I'm sure you know that there are several methods to isolate vesicles from human body fluids, and most widely used are differential ultracentrifugation and density gradients. Now, the first question you have to ask yourself if you're working with complex body fluids such as plasma is the question whether or not you have to isolate the vesicles. On the upper right you see 4 extracellular vesicles present in normal human plasma, but you also see many chylomicrons. Now, for some applications it's essential that you isolate the vesicles, but for others it is not necessary. For example, on the left I summarized a few methods where isolation and purification is absolutely essential, such as small angle X-ray scattering or proteomics. On the other hand, if you perform functional assays, flow cytometry or ELISA, isolation is often not necessary. So please bear in mind what your downstream application is. Now, when people start to isolate vesicles, they often think that what they end up with is what you show in the background, and that is a sample containing only vesicles. Well, this is something that happens only in your dreams when you start with body fluids. So you have to be aware of artifacts and problems along the line. Now, if you start to isolate vesicles from human plasma, and I am using human plasma as an example because it is such a complex body fluid, then you have several problems to face. The first is you have a high concentration of soluble proteins. Plasma has a strange viscosity and high density, making it difficult to isolate vesicles by centrifugation. You have small cells present called platelets, which cause problems because they may overlap in size and density with your vesicles. And of course you have lipoprotein particles and chylomicron present. And sometimes, especially in non-fasting subjects, these are present in very high concentrations. Now, for a decade or so, centrifugation has been used by all labs to isolate vesicles from plasma and other human body fluids. But now we are learning that centrifugation is causing problems. For example, whereas vesicles from erythrocytes do not have a tendency to clump during and after centrifugation, vesicles from platelets will do so, and in fact these clumps are extremely difficult to resuspend. So you have to be careful because you're inducing a sort of loss of subpopulations by centrifugation in the case of plasma. Also, when you try to pellet vesicles from plasma using high centrifugation speeds, what you will see is that protein complexes and also lipoprotein particles may be pelleted. So your pellets do not contain only proteins, not only vesicles, but also proteins and lipoprotein particles. You can also apply density gradients to isolate vesicles from plasma and other body fluids. One of the commonly used density gradients, at least in our hospital, is potassium bromide density gradient centrifugation, and this method is used to separate different fractions of lipoprotein particles from plasma. So you start with plasma and you are able to separate the different fractions of lipoproteins. Now, what you can see in fraction 3 is that this fraction contains the HDL particles, so that's the fraction with the density between 1.063 and 1.21 gram per mil, and this fraction contains HDL particles but also vesicles. And this is simply because both have an overlap in density. So when you apply a density gradient to plasma, you will be unable to separate HDL particles from the vesicles. The other problem is that if you use density gradients, particularly sucrose, these gradients are very viscous and they're hyperosmotic. In other words, they affect the structure and possibly also the function of the vesicles you try to isolate. And in the past it has been shown that if you apply sucrose gradients to isolate organelles, this can be highly deleterious. So please be careful also here. Now to summarize this, if you start to centrifuge plasma, there's a risk that your pellets contain also protein aggregates, you may lose subpopulations and you have problems with viscosity and density. On the other hand, if you apply density gradient centrifugation, your vesicles may be contaminated with HDL. With sucrose you have problems with hyperosmolarity, but of course this is not the case for OptiPrep, so that's by far a better choice, I would say. Of course, both centrifugation and density gradient centrifugation are time consuming and you require centrifuges, rotors, etc. So you require quite an infrastructure to do this. Recently, an old method, size exclusion chromatography, has sort of regained new interest. This method has been used for 20, 30, maybe even 40 years to isolate platelets from human plasma. And this is just illustrated by the publication on top by Holmse. This method was used because platelets were easily activated when they are centrifuged, but by using size exclusion chromatography this is not a problem. This method has also been used in the past, illustrated by the paper of Doug Taylor, and a few years ago we started to use this method again. Just to illustrate you how old and widely used this method is for platelets, if you go to Google and type in platelet gel filtration and look at pictures, this is what you will see. In numerous papers this method has been used in the past. So it's not a new method, but it's a sort of new or rediscovered application. Now on the right you see what we did in the AMC. We took a simple 10 ml syringe, put in some nylon stocking at the bottom so that the gel which you pour in does not come out. The gel consists of Severose 2B, and this system you can use to put on plasma or other body fluids or other fluids containing vesicles, and you can isolate the vesicles and purify the vesicles and to separate them and separate it from the vesicles from the proteins. Now how does size exclusion chromatography work? The gel consists of a sort of little spheres. The spheres are hollow. Small molecules such as soluble proteins can enter the spheres, and the vesicles which are large will not, and the vesicles will migrate along the spheres. So the vesicles will be in the void volume, whereas the soluble proteins will be present much longer on your column. And so they appear in different fractions and they leave the column much later than your vesicles. We published this in a paper in 2014 in the Journal of Extracellular Vesicles, and we showed that if you look at the y-axis you see the percentage of total particles of vesicles, and you see the fraction. We collected fractions of 500 microliter. You see it on the x-axis. You can see that around fraction 10 several methods confirm the presence of vesicles or particles in those fractions, whereas for example, fraction 10, you can see that the concentration of protein and the concentration of HDL are very low. In other words, vesicles are relatively enriched in these fractions compared to soluble proteins and HDL particles. Now, after such a single step, which by the way can be repeated to make your vesicles even more pure, of course you will also be losing some vesicles then, but if you do this, you get highly purified fractions of vesicles that you can use for small angle X-ray scattering, as shown on this slide. You can do proteomics because you have lost most of your soluble proteins. And what speaking for myself, I think is the biggest advantage, you can do electron microscopy directly on vesicles from plasma after a single size exclusion chromatography step. Well, in summary, I think that size exclusion chromatography has not solved all our problems, but regarding purification of vesicles, I think it's a very good manner. It's a very good technique. On the other hand, concentrations of vesicles cannot be achieved during size exclusion chromatography. Size exclusion chromatography does not have the risk of losing subpopulations. It's an excellent manner to get rid of your lipoprotein particles, including HDL. But of course, if you have chylomicron present or large proteins, they will co-elute with your vesicles and you may need other methods there. The recovery is pretty good, and as I said, because you're not losing subpopulations, I think it's a very good manner to isolate vesicles by size exclusion chromatography and, for example, then further concentrate your vesicles by centrifugation. Now, why is isolation of vesicles so important, especially when we are talking about plasma? I think to circumvent artifacts and wrong conclusions. There have been numerous papers recently on the presence of microRNA in extracellular vesicles, also vesicles present in plasma. Now, when you look at plasma, we do know that, for example, microRNAs are present not only in the vesicles, but they can also be associated with ADL particles and also be associated with soluble proteins. So when you apply ultracentrifugation to plasma, you have to be aware that your pellets do not contain only microvesicles, but also lipoprotein particles and some soluble protein complexes. So you have to be careful with your conclusions. And in fact, this is what has been shown in 2014 in a PNAS paper, showing that perhaps most microRNAs in plasma are not present in vesicles. So we definitely need more research there, but if you apply size exclusion chromatography to vesicles and separate them from plasma, also the bulk of the microRNAs will not be present in your vesicles. Messenger RNA is, but not microRNA. So you need a decent isolation method to study the true presence of, for example, microRNAs in your vesicles. Now, we do have several instruction movies, YouTube style, on our website medves.eu. This is a screenshot from one of these movies. This is how to isolate vesicles from human blood using Cephros, and this is freely accessible, so please feel free to have a look. And of course, I would like to thank all the people, in particular Anita Beuing, who did most of this work. I would like to thank everybody for their help and support. Thank you very much for your attention.